Okay, so this is the next question that we got on the menu today, and it is asking us the distance from Earth, that's where we are, to Polaris, and that's a star that's very, very far away. In the night times, maybe you'll be able to see it. So the distance between us is 8.762 times 10. I'm going to assume what that means is times 10 to the power of 18 meters. Okay, so let's actually draw a diagram for here. So let's got our Earth. Hopefully we've all been here at least once. And our distance between us and Polaris. Polaris is a star, so let's draw it as a star. So the distance between us is going to be 8.576 times 10 to the 18 meters. And we're going to assume that this is just a formatting issue. How long would it take to disappear from our vision if it were to, I think that means burn out today? Answer in unit of years. Okay, so essentially, when we look in the sky and see stars, we don't actually see them. We see where they were. Okay, because light takes time to travel, like even this camera. This camera is not seeing me right now. There is a minor delay for the light to bounce off. Light comes from my lamp, bounces off my head, and bounces back into the camera. It takes time for that to happen because light is not instant. Light has a speed, very, very fast, but it still has a speed. So, here it's going to be maybe like picoseconds, like so small that it's pretty much instant. But when you look at distances that are, the like spatial distances, like spaces, like actually what I mean by like in space, those types of distances, light actually does take a while to travel. I think it takes sunlight about 8 minutes to reach Earth. So if the sun were to suddenly just, peace out and didn't want to be, it wasn't all sunshine and rainbows anymore, and the sun just dipped, it would take about 8 minutes for us to even realize that it happened, because that's how long it takes for light from the sun to reach us. So the light is a lot closer to us. The sun is a lot closer to us than Polaris. So this effect will be magnified by a lot. So we expect that this is going to take some delay. Another interesting thing about this is if we were to somehow teleport very, very far away and you looked back at the Earth, you could see yourself in the past, possibly, because of, if you were to somehow travel faster than the speed of light or get to a distance faster than light can, you'd see in the past. That's a very interesting thing to think about. Okay, but that's kind of going beyond the scope of this. We know that the velocity of light, speed of light, we represent it with the letter C. And that's just the way it is. Okay, and the value that we're using here is 3 times 10 to the power of 8, which is typically what you're going to use, right? Sometimes you use 2.99 if you need extra precision, but 3 is fine. So 3 times 10 to the 8 meters per second. So this is the speed of light, and we want to find the time that it will take for light traveling like this to travel this distance. So we know that distance over time is going to give us our velocity. We can also write this as v. C is just what we typically use because the speed of light is so commonly used, but in general it's better to use, or in this type of situation it makes more sense to use v because we're thinking about more of a velocity thing, and we're not going to worry about like time dilation and all that. Don't worry about it. That's Einstein. Okay, so here we want to isolate t. So to isolate t, we're going to multiply both sides by t and divide both sides by v. So d over v is equal to t. And let's sub in our numbers. So our d value, that's our distance, d, 8.576 times 10 to the 18 meters divided by the speed of light, 3 times 10 to the 8 meters per second. Okay, let's do some quick math to figure it out. Quick math by asking our calculator. 8.576 times 10 to the power of 18, all divided by 3 times 10 to the power of 8. And my result for this calculation is 2.859 times 10 to the 10 seconds. Okay, so I'll just represent that with an S. Okay, so that's the time that it will take, but it asks us for our answer in years. So we have to convert this into years. Because I know that that's a long time, but when we think about it in years, we can more contextualize it. Like, how many human lifetimes is this going to take? Okay, so given that we have 2.859 times 10 to the 10 seconds, we're going to do a unit conversion process to get to years. So we know that if we multiply, we have to divide by 60, so 60 seconds per 1 min. And we know that we have every 1 hour we get 60 minutes. Okay, and hopefully you can see like these units canceling out and why that works out. Then we're going to divide it by 24 for 24 hours for 1 day. And we're not going to worry about like leap years and all that. Let's just do 365. Technically it would be more accurate to do 365.246 or something like that. But we'll just use 365 and not worry about light years. I mean, not light years, leap years. So 1 year is 365 days. Okay, so in years, we're just going to divide by 60, divide by 60, divide by 24, divide by 365. Okay, so let's do that math ASAP fast. Take the number that's stored in the RAM of my calculator, divided by 60, in brackets, divided by 60 times 60 times 24 times 365. And my calculation for this is 906.47 years. Approximately. Given that we only had one significant figure in, for our speed of light that we used, we could technically only say 900 years. So 1 SF. So, if you're very lucky, if Polaris was gone, 800 years ago, my grandchildren might be able to realize it, So it takes quite a while. Hopefully we got a similar answer. Yep, they got pretty much the same calculation, maybe with some rounding errors, but that's nothing too concerning. So yeah, this question is good. So the above solution is good. Awesome.